Okay, so I think it is my understanding that from the previous class or from the previous classes, you covered um, viscous flow in terms of shear stress between fluid layers, where you made the assumption that the stress is proportional to the normal velocity gradient. Um, I think you also considered some arbitrary point where the boundary layer ends. That's usually 99% of the free stream velocity. Um, yeah, you considered basically most of the things you did in your fluid mechanics class. Okay, so that same analysis can be applied to a thermal boundary layer. Okay, the same analysis can be applied to find the convective heat properties. Okay, so just as you have it in the hydrodynamic boundary layer, where a region was defined for the flow, where viscous forces are felt, you can apply the same analysis to a thermal boundary layer, which can also be defined as a region where temperature gradients are present and exist in the flow. Okay, and in convection, we're considering heat um, heat loss from a solid surface into a fluid, and then the heat is carried away. Now there are two forms. There's a forced convection, and there's a natural convection. For forced convection is where you have a driving mechanism. You have a pump, a motor, a fan, or something. And then for the natural convection, it's where temperature difference or density difference, some kind of concentration difference affects the movement of the fluid. Okay. So I think that is where you are now. So today we are going to um, be considering the same analysis you made, but this time we're going to look at a flat plate with unheated starting length. Okay. So instead of having the same analysis where you have a uniform thin wall, where you look at the different phases of transition of flow, we'll look at the same thing, but this time we're looking at a plate where the heating is not at the starting point. Okay, so let me focus this. Let me draw something here. Hold on, let me focus this. Okay. All right. So let's assume that we have a thin plate. Okay. So assume this is our thin plate, and we have a velocity boundary layer that goes this way. Okay. And then we have a region that is unheated. Okay. Let's call this zeta. Okay, this funny looking Greek alphabet. Okay, and then we have this heated region. Okay, so we'll have this will be a velocity boundary layer and thermal boundary layer. Okay. Now, there are some important assumptions to make here. We can assume that the velocity boundary layer starts to develop right from the edge here at x equals to 0. We have our velocity boundary layer starting, okay? And then we assume that a thermal boundary layer starts to develop at x equal to zeta at some point here, okay? will be our thermal boundary layer starting point. Okay. Now, the heated section at which X is greater than zeta and everything after it, we're not going to go through the same derivation that you did. Okay, I'll just write down the Nusselt number, okay, for both laminal and turbulent fluid flow. So the Nusselt number for this region is given by Nu at X, where this is equal to 0 and divided by 1 into the value here over X raised to power 3 over 4, all this raised to power 1 over 3. Now, just to make you appreciate what is going on here, there's a lot of math that went into coming up with this expression, okay? I just brought my textbook here. I just want to show you just an example of a derivation process to arrive at this expression, okay? So if you have this analysis, let me just show you this. So if you have a thermal boundary layer, just like we have in this diagram, you can make a connection between the conduction, the amount of heat lost by conduction from the plane that we're considering into the fluid. Okay, if you relate them, you get a value for H, and then you make some boundary layer assumptions. Now, these are the assumptions that we use to come up with the first expression. Okay, a lot of math goes into it, and then we arrive at this. This is what we get. Okay, the only thing here is that we replace this expression by Prandtl's number. Okay, now if we get this final expression, we can then go ahead and make some other boundary layer assumptions to get the expression I just put down on the paper. Now, this is the expression I wrote down, okay? 0.332. Now, this is coming from making some very calculated boundary layer assumptions, okay? You don't have to worry about the math, but I just want you to understand where that is coming from, okay? So it doesn't look too much like magic. Okay, so where Nu X as zeta equal to 0 equal to 0.332 multiplied by the Reynolds number at X raised to power 1 over 2 multiplied by Prandtl number raised to power 1 over 3. So this is the expression for the laminar flow for the system that we are considering, okay? And if we consider that the flow is turbulent, once again from a series of calculations and experimentation, you get this value. Now, once again, it is a consideration of most systems boils down to your initial analysis, okay? Whatever analysis you do on your system determines if you think it's a flat plate with unheated starting length or uniformly heated flat plate. It always comes down to that. So if you can be able to do this analysis and come up with the right conclusion, then you'll be modeling the accurate system. Okay. So now for the average Nusselt number over an entire plate of length L, um, we can go ahead and derive another expression from numerical integrations. Okay, I think you all have the note. If you don't, I think the professor posted a note on the website. So you can go ahead and download that note just to see, just to follow along. If 100 at zeta equals to 0 into L over L minus L here being the entire length. Okay. Minus 2p plus 1, 2p plus 2. Okay. Now, this is the consideration that the Nusselt number across the entire plate is even, is the same, or is average over the same, over a certain distance. Then we will assume that P, this value in this expression for laminar flow, we'll assume that P is equal to 1, or we'll take it that P equals to 1, and NU, the Nusselt, the average Nusselt number across the plate would then be equal to 0.664 multiplied by the Reynolds number of the length of the plate raised to power 5. Okay, now this, you have these expressions in your textbook, and once you make the analysis and you come to a conclusion or a consensus on what you think the system is, most times you just have to pull these formulas out and use them in your calculations. So now, if we substitute the value of this expression, okay, into the portion of the plate that is heated, which if we assume that this is, hold on, this is L, the entire length of the plate, then the part of the plate that is heated is L minus zeta, right? So if we apply this same analysis that we've just done and apply L minus zeta, we get that the rate of heat loss will be equal to this minus, we already know this expression, right? Just that this is, we're just considering the heated region, okay? Only the heated region. Now, if we continue this and say, let's assume that we have uniform heat flux. Now, let me show you this diagram again. Okay. Now, in this expression, in this design, if we have uniform heat flux across the plate and we'll still have our velocity, okay, our initial velocity and the initial temperature, which is the temperature and velocity of the surrounding fluid to the region of consideration, then we can also go ahead and come up with an expression for the laminar and turbulent flows. Okay, the Nusselt numbers for those considerations. Okay, this will come in handy for certain systems that you're considering, okay, that are under uniform heat flux. So the expression for this also Now, once again, there's a lot of math in the background, okay? But we can afford to just write them out. This is for laminal, and then for turbulence, we have this to be x 0.028. Okay. And we know that, I mean, from your knowledge of fluid mechanics, for turbulent flow, the value of Rex has to be less than 5 exponential, 5 exponential 5, right? You also have to have this. Okay. Now, is there any confusion so far? I hope all this makes sense to you. Okay. So, if we consider I already wrote down an expression for what the heat transfer or loss from the plate will be. Okay. Now this considers um, the convective side of our expression, right? Where we have the temperature gradient, we have the area, but we're considering only the heated region, right? Now, if in this new expression we are considering a uniform heat flux, okay, I can also write a rate of heat loss or heat gain, depending on what the system is doing, okay? I can expand this to become this. Where A is the surface area, and then Ts is the surface temperature. Okay. Now I'm just writing down formulas. I'm just making statements, but we can get to test these formulas in an example. Okay. So in your notes, there's one example there. I'll just read it out. I hope you have your notes with you. So the example says engine oil at T infinity. Right, example one. So engine oil at T infinity equals to 60 degrees Celsius flows over a 5 meter long flat plate with Ts equal to 20 degrees. So we have 5 meter long flat plate. We have Ts to be equal to 20 degrees Celsius. Now, if the velocity is equal to 10 meter per second, this is the velocity of the fluid surrounding our area of consideration. Find Q dot per unit width of the plate, okay? Q dot per unit width of the plate. Now, like I said, you have to first of all consider what kind of system you're dealing with, okay? Are we working with a uniformly heated plate, uniform heat flux, one part of the plate heated and one part of the plate not heated, okay? So, but first of all, so for every system that we have discussed, we have a laminar and turbulent analysis to it, okay? This is for a flat plate with some part of it heated. This is for uniformly heated flat plate. This is for uniform heat flux. each one of them have a laminar and turbulent formula. Okay. So now this question says that engine oil flows over a flat plate. The temperature of the surface is 20 degrees and T infinity is 60 degrees, right? So we have a temperature gradient flowing into our flat plate. Okay, there's nothing in the question that suggests that only one part of the plate is being heated. There's nothing in the question to suggest that we are dealing with a uniform heat flux system. So you can see that apparently we are going to have to use this analysis. Okay, I hope this makes sense to you. So the first consideration is we are going to take some region in the fluid, which will be the center of focus for analysis. Okay. Now we're going to find the properties of the thin film. We're going to consider a thin layer in our fluid and check the average temperature. Okay, so let's say TF, which is a thin film temperature, is the average between the surface temperature and T infinity, which is 60 degrees Celsius plus 40 degrees Celsius divided by 2, and that gives us 40 degrees Celsius. Okay, so this is the region where we're going to make our analysis of. Okay, and we have standard values for the fluid at this region. Okay. So all you have to do now is go into your textbook and then take out the values of interest. We are going to need rho, which is the density. We're going to need specific heat. We're going to find out the velocity of the fluid at that region also.
Hey, Vincent.
Yeah.
Would the average be 50 degrees C?
Thank you.
Oh, I'm sorry. I made a mistake here. Sorry about that. So TS is 20, not 40. Okay. So my brain was thinking it, my hand was writing something else. Sorry. Thanks for that though. Yeah, so and then also Prandtl number for engine oil. So can you please take a look at your table? I think it's table A13, as you can see in the notes. Let's just pull out the values and make sure we're doing the right thing. Okay. So if you have the textbook, please check table A13 and give me the values for engine oil. Okay. Is anyone doing that?
So the density, what temperature are we looking at?
At
40?
Celsius, yeah.
Yeah, so the density will be 876.0. The specific heat will be 1,964.
So what is the
units?
Yeah, the units for this.
So for the specific heat, it's joules per kilogram Kelvin. Okay. And then the density is kilograms per meters cubed.
Yeah, okay. Yeah, I think I figured that.
And then
the
is that the dynamic viscosity?
Mm-hmm.
The dynamic viscosity is 0.2177 kilograms per meter second.
0.277?
2177, sorry.
Okay.
And that was kilograms per meter second.
Okay.
And then the Prandtl number is 2,962.
Okay, how about the value for K?
Oh, The thermal conductivity is 0.1444 watts per meter Kelvin.
Okay. Okay, is that all we have there on that table?
It lists the kinematic viscosity.
Okay, and what's the value?
Kinematic viscosity is 2.485 times 10 to the minus fourth meters squared per second. And then it also has the thermal diffusivity. Do you want that?
Do we need that? No, I don't think we need that.
And then it also has the volume expansion coefficient.
No,
Okay.
I don't think we need that. Yeah.
That should be everything then.
Yeah. Okay, so we do know that this is we're assuming that we're dealing with a uniformly heated plate, but we still don't know if it is laminar or turbulent. Okay, and we can easily check that by looking at the Reynolds number for the entire length of the plate. Okay, and do that by multiplying the velocity outside the fluid for the surrounding fluid multiplied by the length of plate we're dealing with and value for V. Okay. Okay. So, and this comes out to what was the value for this? 10 meter per second multiplied by 5 meters divided by 2.485. I hope our values, okay, yeah. Our values are, the units align, okay. And this gives us, this is 50, and we should get something in the range of, can you compute this real quick? Hey, do you have a calculator there? Is anyone computing this? Times 5.
So I got that it was 201,207.
201,000?
Yeah, 207 after that.
201. Okay, and 201, that's 5 zeros, right? 2.01 multiplied by 10 raised to the power 5. And clearly this is lower than 5 exponential 5, right? So we're dealing with a laminar system, okay? And so we just go back to our system consideration and look for the laminar, the formula for a uniformly heated plate for a laminar system, which is this, okay? So I'm just gonna put that down real quick. We have a Nusselt's number to be NU equal to 0.664 multiplied by REL, let's go 0.5, ER, raised to the power 1/5. Okay, so we already verified our system is laminar, so all we have to just plug in our value here. We know what these values are, and that gives us 0.664 multiplied by 2.01 times 10 raised to the power 5 raised to the power 0.5 multiplied by 2962. Let's go 1/5. Okay. We're terribly behind time, so let me just open this up and get out the value from the notes. So this gives us, please just try and compute this just so we can verify that we have the correct values in the notes, okay? I'm just gonna write the value from the notes. If you get something else, please let me know, okay? I know we also have this expression, which you did you must have done in one of your past classes, just so we can be able to compute the rate of heat loss. Okay, we need our H value. And from this, we can get that H is equal to the Nusselt's number multiplied by K divided by L. And this gives us 4277 multiplied by our value, which we got from our table, which is 0.144. Yeah, 0.144 Kelvin. Okay, and then all this divided by 5. Okay, and we get 123.5 watts square Celsius or Kelvin. Okay, so that becomes our value for H. Okay. And computing Q becomes straightforward now. Okay, so now to find we're not just finding Q, right? We're finding Q by units width, right? So just go ahead and divide that right away so that we don't have to compute it and come back again. But we know that we already had an expression for Q, which is HA into T infinity minus TS. Okay? Just divide all this by the width also. Now we know this to be 123.5 multiplied by our area. Now the area is going to be 5 multiplied by the width, but we're also dividing by the width. So we can just go ahead and multiply by 5, okay? And then multiply by the difference in temperature, which is 60 degrees Celsius minus 20 degrees Celsius. If we compute this now, we get 24706, okay, watts per meter. We're dividing by the width, okay. So this is our answer. You can simplify it by converting it to kilowatts. All right. So that's for the example. I just want to run through that second example before we run out of time. This class is for 1 hour, right?
Yeah, it ends at 10:50.
Okay, so we just have little above 14 or 15 minutes more. Okay, so the second question says a flat plate of width 1 meter is maintained at a uniform surface temperature. That phrase right there just makes it very simple for you. So it says it's maintained at a uniform surface temperature of 215 degrees Celsius. Okay, so surface temperature is equal to 215. Okay, so 215 degrees Celsius. And by using independently controlled heaters, okay? So each heater is 50 millimeter long, and the temperature of the air, T infinity, is equal to 25 degrees Celsius. The outside air velocity is equal to 60 meter per second, okay? So the question says, find the heater with the max electrical power input. Okay. Now, there's a diagram for our heaters. So we have a couple of heaters, okay, that are each 50 millimeter long. And they are all controlled independently, okay? And the entire width of the plate is 1 meter. And we're going to find which of these heater is contributing the largest amount of power. Now, if you relate this heating plate to the analysis which we have done so far, then we can use the rate of the condition of the flow over each heater to determine which of them is working the hardest, okay? So we did the analysis where we say we're assuming a flow, we're comparing it to hydrodynamic flow. So let's do the same analysis on this plate this way, right? And there's a transition phase, right? It's moving from laminar to turbulent, okay? So if we do the same analysis, we can then evaluate at which point the heater is working the hardest. Now, just like we started the last question, let us take the average point in our fluid thin film, the thin film phase that we're going to be considering. And we can find out by taking an average of the surface temperature and the temperature of the surrounding air, okay? So the thin film temperature will be equal to Ts plus T infinity divided by 2. That is 215 plus 25 divided by 2. That's 220 plus, that's 240 divided by 2, which is 120 degrees Celsius. Okay, so once again, so we are short on time. Let me just read out the values from the notes. So these are just confirmed from the table if you can, to make sure we don't have any value written wrongly. Okay, a specific heat. Is this 0.7? Well, that's small. Anyway, so now in this analysis, we can't just go straight ahead and start considering if it's a uniformly heated plate, because our plate is divided into regions. Now, the point here is we want to know at which point laminar flow starts transitioning to turbulent flow. okay, so that we can know which of these points requires the highest amount of Q coming into it, okay? And to do that, we can use the critical point formula to know at which point it is transitioning into turbulence, okay? Now, if you remember from fluid mechanics, that formula is X equal to, take that, RE over the U infinity, okay? We have everything we need to evaluate this formula, right? So 2.522 times 10 for 5 multiplied by the critical point.
Hey, Vincent, can you slide it down a little, please?
Oh, sorry.
Thanks.
Yeah, keep taking my eye off the screen. Okay, so multiplied by 5, the critical point 5 times 10 raised to the power 5, and divided by the given velocity of outside fluid, which is 60 meters per second. Okay, so if you compute this, you get X to be 0.2 meter. Sorry, I just have to read this off the note because of time. Okay. So if we know that each we know that the length of each heater is 50 millimeters, right? So if we stack them side by side, okay, let's say the first one, second one, third one, and then fourth and fifth. This is 50, 50, 50, 50, 50. 1, 2, 3, 4, 5. Okay. So 50, 100, 150, 200. If you convert this to millimeters, you get 210 millimeters. Our transition phase will happen in the fifth heater. Okay. Transition to turbulence starts from X equal to 210, and that falls on our fifth heater. But we still have to go further to find, just to understand the nature of the fluid flow around that fifth heater, moving from the first heater, okay? So the question is trying to find which one will have the maximum power, okay? Now, we can't just make a rough approximation like that. We have to look at what is happening from these 2 points, at the start point and at the point where we are transitioning, okay? Now, in order to do that, we need to look at what is happening at heater 1, heater 2, and after heater 1, heater 5, and after heater 5. Okay, so at heater 1, remember that the amount of power being consumed by the electrical power being consumed is equal to the amount of heat or loss or gained by the convective energy by convection. Okay, so we have Q for the amount of electric power is equal to the Q convected away. So now for heater 1, let's compute Q dot. Get this to be H1 L1 multiplied by the way Ts minus T infinity, right? To find the amount of heat convected away. Okay. Now we have to find what kind. Now we can go ahead and find what kind of system we have at that point. Now that we have sufficient information. And to find the system, we'll have to check once again with the Reynolds number, okay? Just to know what kind of flow, although I can make a rough guess and say that we have laminar flow at that point. Okay. Well, so multiplying this, we have our length to be 50 millimeters divided by 3. We have 0.005 meters. Okay, multiplied by the outside air velocity second, and then divide this by the value that we got from our table. Okay, which is 2.5 to 2 times 10 raised to the power minus 5 n squared over s. Okay. Once again, I'm just going to write this from the notes. Please confirm, make sure we have the right thing. Okay. 1.19 exponential 5, which is way less than 5 times 10 raised to the power 5. Okay. So we definitely have laminar flow at that point. So now that we have confirmed that we have laminar flow for a uniformly heated plate, nothing in the question states otherwise. So it is a uniformly heated plate, laminar flow. And we already established the formula for that kind of system, which is 0.0664, 0.664. That's the formula we're going to use. So we'll find a Nusselt's number using that formula, which is 0.664 multiplied by 65. Okay. Okay, so we have that at that point. Now we're going to try and find the heat, the amount of heat lost or gained at that point. And in order to do that, we have to first of all find H. Once again, use the expression for H. Okay. So this is equal to 204 multiplied by 0.3235. This is the length of this is where the heater one ends, 0.05, 50 millimeters. Okay. We get H to be 132 watts per meter squared Kelvin. Okay. And then we can evaluate Q and find Q to be 1,250 watts. Okay. So we can go ahead and we have 2 more minutes. Let me just bring the notes and just run through this, okay? Just so that you understand what is going on. Now, to find the heat transfer at heater 5, we can use this clever trick just to be able to find the value of Q, because we don't have everything, because we're moving from left to right. Now, we know that the value for the heat transfer lost at Q is equal to the value of Q from 1 to 5 minus the value of Q from 1 to 4. Okay. Now, if you put that in this formula, if you express it and multiply that, we can put all this in one bracket. Okay. And this is equal to 4 times the Reynolds number at 4 times, because we have 4 of them. Okay. And we already know what the Reynolds number is for heater 1. Now, if you multiply this, you will still get this to be laminar. It is so it confirms the calculation that we did earlier to show that it's laminar all the way to the 5th heater. Okay, and then we can evaluate the Nusselt's number. Okay, and find our H. And once you get H, you can then calculate and find Q5. Okay. So we now know that it is laminar all the way from heater 1 to heater 4. It starts turning into turbulent at heater 5. So we have the value at heater 5, we have the value at heater 1. All we have to do now is find the value at, like, when it starts becoming more turbulent, which is after heater 5, right? Which will be like heater 6 and upward. Okay. So if you evaluate that, you come to this conclusion, and if you put them together, you discover that the Q for heater 6, where it starts achieving turbulence, is the highest value of Q. Okay. So I hope this makes sense. Sorry, I had to run through the last parts, because of time. Are there any questions? Is this clear to you? Like, do you understand what is going on?
Yeah, it makes sense.
Okay. So yeah, once again, thanks guys. I hope I was able to make myself very clear, and hope I was able to help. So, thanks for coming to today's class. I guess we'll see again next week. I hope I just have a question. I hope the assignments, have you seen your graded assignments?
Yeah.
Okay. Don't hesitate to send me an email if you don't understand something. If I left a comment and it doesn't make sense to you, just send me an email, okay? So have a nice rest of the week, guys. See you next week.
Thank you.
Yeah, thank you.